name's Casey Rutland. I'm an Associate Director and Architect at Arup Associates and part of the team that created Project OVE. Project OVE is our answer to trying to find a BIM exemplar project within Arup. It's a project based on the human body. It maps human body systems to building systems, and then we try to replicate that using software to design and prove that a building will work. It's a tool and a project that we can use to test software, to train our staff, and to allow us to demonstrate what we can do with BIM to people external to Arup, graduates and apprentices, as well as our own staff.
My name's Andrew Duncan. I work in Building Engineering London for Arup, and I originally led the Project OVE team. To us, Project OVE provides an opportunity to build a case study to prove the benefits of BIM internally and externally. It's really important to show different parts of the business what they can use BIM for, and to create tangible examples that they can actually refer to in the future.
In addition to standard pieces of software such as Revit, Tekla, GSA and Rhino, we use a number of in-house developed tools and apps to make all these pieces of software communicate with one another.
So we started with me being scanned, which was fun. Then everybody else took away that scanned data and turned that into a mesh model, which we then took into Rhino, cut contours through. From there, we took that into Revit, created Revit geometry that allowed us to create a dynamic facade. We filled it for building services and structure, again using different platforms. We used GSA for the analysis, Tekla for the structural model, Revit for the building services. So we weren't really bound by any particular software, just my initial scan. We were able to use the standard functionality in Revit to create Revit systems and pipe systems, which is nothing revolutionary. However, we embedded formulas and lookup tables into the families that we used in the project that automatically calculated the heating and cooling loads in each of the bits of the equipment, how much chilled water and HHW flowed through those equipment, what the acoustic performance of that equipment was, what the throw of the air terminals were on the ventilation systems, all through just changing the air terminal flow rates at the end of the systems.
In order to realise the final model and the data set, we had to bring together several different disciplines, different types of engineering throughout the Arup group.
We had structural engineers, electrical engineers, PH, mechanical, an architect, all sorts of people inputting into the process, which is really a strength of Arup, being a big multidisciplinary company. In order for us to actually do something useful with the project, we couldn't just model me at my height. We had to blow it up into something a little bit more realistic. So we chose a 35 story, 170 metre tower. That provided some interesting challenges in terms of structural calculations, but it really gave us a blank canvas to work with. So to put the scale into some context, it's roughly the same size as the Gherkin, another Arup project. We worked out that the building, if it were to be built by a real client, would probably be the world's most expensive building on actual usable floor area, predominantly because we filled it up with a whole load of building services to replicate the lungs and the heart and brain and so on. So it's a bit of a squeeze actually walking around, but it does actually function as a real building.